Hello everybody. In today's class, we shall discuss parity generation and parity checking. What is parity and how is it useful, that we shall also discuss in this particular class. So, we shall begin with a discussion on exclusive OR gate and then we shall go on discussing the parity, its generation and checking. Exclusive OR gate follows a truth table as you see over here. When this is a 2 input exclusive OR gate, when A and B both are of same value, say 0 0 and 1 1, then the output is 0. Okay? And when one is 0 and the other one is 1, these two cases the output is 1. This is what is exclusive OR truth table. And how we represent it? We represent this as A prime B, okay, product term, and this is as A B prime. So, we simply sum them up and then we get the exclusive OR function, logic function. And the symbol that we use for exclusive OR is A XOR B. I mean, this is one particular symbol which is equivalent to what you see over here. Okay. For simplicity, for a compact representation, we can use this symbol. Okay. Realization is very simple. So, you will be generating A prime B and A B prime, okay, through NOT gate and AND gate, and then we will sum it up. And if you are interested to realize it using only one type of universal logic gate, which is NAND gate or NOR gate. So, NAND gate is useful. We can use 4 NAND gate, a combination like this, by which we can get A prime B and A prime B plus A B prime over here. Okay, you can check it yourself by. So, basically this is A prime B prime is A B prime you get AND gate. So, from De Morgan's theorem A prime plus B prime. So, you can go on breaking it up in each of these cases, this NAND function, and then you shall see that this is what you get. Okay. So, exclusive OR logic gate has got a symbol. So, this is the symbol for 2 input exclusive OR logic gate, and in this case we know from this truth table, if any of this input is say B is say 0, see if we put it 0, okay, then output follows the input. What is this case? This is the case B is equal to 0, B is equal to 0. So, whenever A is 0, output is 0, A is 1, output is 1. Okay. And if B is equal to 1, that is 5 volt if you connect, okay, what is this case? These two cases are there. So, when A is 0, B is 1, Y is 1, A is 1, Y is equal to 0. So, the opposite of it. So, A XOR 1 is A prime. Okay. So, this we take note of. Okay. Now, multi-input exclusive OR gate. This is useful in our parity generator and checker circuit, which we shall see later. So, multi-input exclusive OR gate, we look at one example where A, B, C, D, 4 inputs are there. So, A, B XORed over here, C, D XORed over here using the 2 input exclusive OR logic function, whatever way we realize it similarly, and then Y is realized by these two. Okay. So, this is a 4 input exclusive OR gate where I mean symbol as a symbol we can represent it in this manner. Okay. So, what is the corresponding truth table? So, this is the 4 variable truth table. So, 2 to the power 4, 16 possible combinations of the input will be there. So, in the beginning we see where A is all 0. Okay. So, if A is 0, just before we have seen one of the input is 0, then Y follows the other input. So, B XOR C XOR D, this is what it follows. Okay. And if A is equal to 1, it follows the B XOR C XOR D its prime. Okay. This is what we have just noted. Now, let us look at the truth table. So, if A B C D is 0 0 0 0, so 0 0 and 0 0 over here. So, A XOR 0 0 XORed is 0, this is also 0, the output is 0 0 XORed is 0. Okay. If it is 0 0 0 1, this line, so 0 0 0 1, this is 0, this is 1. 0 and 1 XORed is output is 1. So, you see the output is 1, right. So, this way if you see that if one of the input is 1 out of this 4, the output is 1. Okay. So, if two inputs are 1, for example, let us consider this particular case. Okay. So, 0 1 0 1. So, 0 1 and 0 1. So, this is 1 and this is 1. So, 1 1 both are of same value. So, the output will be 0. So, when 1 1 the output is 0. Okay. So, we can take up any other case where there are two ones, say A and D, or AB and AV are 1 1 and CD are 0 0. So, 1 1 and this is 0 0. So, this is 0, this is 0, the output is 0. So, you can look at all possible cases of two ones appearing, you will find the output is 0. Now, let us look at three ones, a case like this. So, A is 0 and B, C, D are all 1. So, this is 1, this is 1 and this is 1. So, 0 1, this is 1, 1 1, this is 0. So, 1 0, this is 1. So, that way if you continue, you will see that whenever the number of input in the combination is odd, okay, number of ones in the input combination is odd, then the output is odd, else the output is 0. Okay. This you can verify, you can check from the truth table, and this happens for 2, 3, 4, 5, 6, as many number of you can have inputs, it will be like this. You can check for yourself a case like this. So, 3 input case. So, this is A, this is B, and then this is taken to, this is your Y, this is your C. You will find the similar thing happening. So, A is equal to 0, A, B, C. So, basically 3 input case, this is the example. You will see that exactly this similar thing is happening. Okay. So, this is we take note of, which will be useful in our parity generation and parity checking circuit that we are going to discuss. Okay. Now, we first define what we understand by parity. Okay. Even parity and odd parity, there are two types of parity. So, even parity means in the input bits there is even number of ones that is present. Okay. So, if you look at the number of ones that are present, if you count them up, okay, in that particular group, and if you see that it is even number, then you say that that particular group has a even parity, has an even parity. For example, this is example for 4 bit group of 4 bits. So, 1 1, 2 ones are there, so it is even parity. Here 4 ones are there, it is even parity. Okay. So, all 0, that is also considered even. Please remember, if there is no 1, all 0, that is also considered as even. For 8 bit combination, you can see this is 1 2 3 4, this is even parity. So, this is 4 and 2 6, this is even parity. Similarly, for 16 bit combination, you can count them up and you can see if it is even, then it is even parity. And odd parity is just it's similar, where the input bits, if you look at the number of ones that is present, if you count them up and if it generates an odd number, then it is odd parity. So, the examples are for 4 bit cases. This is odd parity because only one input is present. So, 1 is present, 3 1 is present here. So, this is odd parity. Similarly, the other two cases, if you can count them up, for example, this is 16 bit input 1 2 3 4 5 6 7 8 9. Okay. So, 9 ones are there. So, this is having a odd parity. Okay. Now, how does it help? What is it? I mean, if you have in a particular group, even parity or odd parity, a particular parity in the particular, then how can it be useful? So, if we know a priori particular group which is particular bits, combination of bits which is sent from one place to another has got a predefined parity, say even parity. Okay. Then during transmission, because of noise, interference or some other thing, if one of the bit becomes erroneous, that means it changes. Okay. So, one of the 1 becomes a 0. What will happen? the parity will be changing. So what was even parity will now become odd parity. Okay. Similarly, if one of the 0 becomes 1, that is also going to happen, right. So if one bit changes, then becomes erroneous, we can detect that there is an error. So what was supposed to be even parity is not even anymore, it has become odd. And similarly, for if it was supposed to be odd parity, we can see that it has become even. Now if more than one changes, so 2 changes, 2 bit changes, then it will come back to the same thing, right. So but the likelihood, the probability of more than one bit changing in a group is much less when the practical transmission of binary digits from one place to another. If we consider that probability is very less. So usually you can see a group of like this, only one bit may become erroneous occasionally, but if you can detect by this method, then you can ask for retransmission or correct it by some other mechanism. Okay. So here is an example where Texas Instruments line transmitter and receiver are designed, and it is tested for bit error rate less than 1 per 10 to the power 12 bits. So you can imagine that this doesn't happen very often. In certain cases, certain kind of noises it might happen, but for that we have got different way to handle that thing, which we may study in digital communication course in some other context. So we are looking for having a predefined priority and checking it, so that any error because of transmission noise or so, we can detect it and possibly correct it through retransmission or some other means which we can discuss later. Okay. But the message that we have in the first place is random in nature. Okay. So if there is a 8-bit message, that means that message can have even parity, can have odd parity, it can have many different things. Okay. So we do not know for sure that whether it is having a even parity or odd parity. So we have to enforce in that group by some mechanism a specific kind of parity. Okay. So that will help us, and from the receiver side it will be known whether a specific particular parity is being followed or not. Okay. So how we can do it? So one example we can see, one way of doing it is, these are 8-bit numbers, okay, that is message bits x0 to x7. So we send it through a 8 input XOR gate, okay, 8 input XOR gate. So what will be the it output? If there is a even parity here, the output will be 0, and if there is a odd parity, that means number of ones present is odd, then the output will be 1. That we have checked, we have seen XOR gate truth table. Okay. So if this is even, right, then this is 0. So if we consider include x8 in that particular group, so right now instead of 8-bit we are sending 9 bits. Okay. So x0 to x7 and additional x8 as priority bit. Okay. So this x0 to x7 has even and x8 is 0. So altogether it is even. Fine. That is what we understand. Now if x0 to x7 is odd, okay, odd means odd number of ones are present, and x8 at that time, since it is odd, this will be generating a 1 over here. So this one and odd number of ones that is present between from x0 to x7 together, it makes even number of ones. So either way, whether these 8 bits are having odd number of ones or even number of ones, this x0 to x7 together with x8, the whole group of 9 bits will always have even parity. Okay. So this is what we can employ to enforce a even parity in this particular message transmission. Okay, irrespective of even or odd number of ones present, the group x0 to x8 will always have even parity. Is it fine? So, from the transmitter it is when told, so receiver will know that it is even parity, it will check. If it is not even parity, okay, then you know that this particular group there is an error. Okay. So, instead of even parity, if the transmitter and receiver they decide on odd parity, okay. So, then how to generate, how to ensure that the particular group of 9 bits will be having odd parity. So, what we will do? We will just put earlier this XOR gate, after that an inverter. Okay. So, what does it do? So, if there is an even number of ones present, even ones present, okay. So, this output will be 0, right, this output will be 0 and it is inverted. So, this output will be 1. So, even 1 and another 1, right. So, ultimately it is a odd number of ones are there, and if instead if odd number of ones are present, right. So, this output will be 1 and or not after inverter it will be 0. So, odd 1 and 0. So, total it is odd. So, this group will be having a odd parity in that group of 9 bits. Okay. So, this is what you will do for parity generation. Okay. Now, to check parity, what will you do? So, similar to what we had done for XOR gate. So, for checking odd parity, we shall send it to a 9 bit 9 input XOR gate. Okay. So, if odd number of ones are present, this will be generating a 1, okay. This will be generating a 1, and if even number of ones are present, this will be generating a 0. Okay. And instead of this XOR gate, if we put a NOT gate after this, inverter after this, then if odd number of ones are present, this is 1, okay. And after that, because of the inversion, there will be it is 0. So, if this output is 0, you can say for sure that it is odd number of ones are present, even number of ones are not present. Even parity will be detected when this goes 1. So, this goes 1 when this goes 0, and this is 0 when even number of ones are present over here. Clear? Right, it is very simple. So, same XOR gate which was doing a parity generation can be used for parity checking also, just by making a proper understanding of input output connection. Okay. And this is just a simple example of 16 bit odd parity checking. So, these bits are present, right, and you can see 1, 2, 3, 4, 5, 6, 7, right. So, 7 ones are there, the output will be, because it is just XOR gate. So, the output, because odd number of ones are present, 1. So, you can check and you can find that the output is 1. So, odd parity is detected in the input group of 16 bits. Now, that was the theoretical or conceptual development part. So, IC 74180 is present as an integrated circuit. So, this particular chip actually does the function of parity generation as well as checking. So, this is a 9 bit, out of which 8 are data bits, 1 is parity bit. The parity generation and checking both it can do. Okay. So, you can see that x0 to x5 and then x6 to x7, right. So, these are the data bits, and there is a even input and odd input, which I shall discuss what it does, and this is a summation of even output, summation of odd output. Okay. So, that means it is basically giving the odd parity, even parity output, the final one. Summation means whether the summation of 1, summation of G, that is what it is considering, and the rest is VCC and ground, the power and ground. Okay. So, its truth table is like this. So when this even input and this odd input, if both of them are high, okay, which should not be the case for normal operation, isn't it? If the input is even, okay, from the previous stage, it cannot be odd, or if it is odd, it cannot be even. So both of them are high means both it is even and both it is odd. It is not practical. So that is not, if these two are both of them are high, it is not doing normal operation. So at that time both the outputs are low, and if both of them are low, the outputs are high. So this is how the truth table is arranged, and irrespective of the other cases what is happening, the summations etc., we don't bother, the output is kept like that. Okay. Now if even input is high, that means previous stage the input side it is high and odd is low. So this is a correct proposition. So if one is high, another has to be low, right? And if the summation of, so basically then the previous stage, the input side it is said that it is even parity. Okay. So if the summation of ones, H means ones, in x0 to x7 is even, right? So input is even, this is also even. Okay. So then what will be the output? Output will be even parity will be detected, even parity will be high and odd parity will be low. So these even output will be high and odd output will be low. Is understood? And input is even and summation of bits is odd, then output will be odd. Okay. And if input is odd, okay, if input is odd and summation of ones is even, then odd and even together the output will be odd. Okay. And if input is odd and summation of ones is odd, then put together the output will be number of ones, it will be considered as even. So this is how the truth table is of IC 74180 works out. Okay. So let us see how IC 74180 in practice works. One example. So in this case, what we see is the x0 to x7 are the data, okay, in which we are checking the parity. So data is transmitted. We are just tapping it and putting it to the IC 74180 data input. Okay. And we have put odd input to the 5 volt. So it is considered this is 1, and even input to ground. Okay. So what we are checking now? By this, if we check, we are checking, if we look at the odd output, what will we see? So if this is even, summation of ones are even, okay, and since odd is kept here, odd input is kept as high, so even and this is odd, so even number of ones here and odd is there from the previous stage or from the input side, so even and odd together it is odd. Okay. So this will be high. Okay. And if this is odd, okay, so odd and odd, this is 1, so put together it will be 0, right. So this is what it is doing when we are talking about it, the checking of it. Okay. And when it does the generation part, checking part we have understood. Now when it does the generation part, if this is even, right, because this is odd, so it will make it odd. So this even and this one together, it will be odd parity, put together, all of them together. Is it clear? Even number of ones are there and this is 1, because of which the output will be odd. So if this x8 is included here, x8 is included here, so this is even and this is 1, so together it will be odd. Okay. And if this is odd, and this odd is high. So this is 0. So x8 now is 0. So this is odd and this is 0. So put together it will be odd. So this can be used to generate odd parity in that sense. Checking as well as generation, both are possible in this manner. Okay. Right. So we are saying that if we are, this IC 74180 can be used in cascade also. This even input odd input that can be utilized properly. So this is also getting higher order from multiple lower order. So basically we are, in this case we are looking at checking 16-bit parity. Okay. So we are getting a 16-bit parity checking done by using two IC 74180. So this is X0 to X7 and this is X8 to X15, right. So this is the lower order and this is the higher order. Put together it is a 16-bit parity checking that is done in this example. Okay. So to start with, you are making it even the input side, because there is no previous stage. So even is considered as high and odd is considered as a low. Okay. So whatever is the number of ones here, that is going to decide the final output. So in this stage, whether it is even or odd, that is decided by these two. Within this particular group, whether it is even or odd, it is decided by these two output. So if it is even, number of ones are present, this will be high and this will be low. Okay. So this is high and this is low at that time. Now in this particular group, even 8 to 15, if it is also even, okay. So even, and this is even in high, so the output will be, this one will be high and this one will be low, right. But if in this particular group, this is odd, say example, this is odd. So this is 0 and this is 1. So this will be 1 and this will be 0 and this is even. So as a whole, 16 bits will be of odd parity, because odd X0 to X7 odd number of ones are present, X8 to X15 even number of ones present. So total is odd number of ones are present. Okay. So at that time, odd is 1, odd in is 1, even in is 0. So this is even. So you will get put together odd out is 1 and even out is 0. Okay. So this is how it works, and you can add more number of stages to get larger number of this thing. And if you are looking for say 12-bit parity checking instead of say 16-bit, right, then the higher 4 bits, right, X15, X14, X13 and X12 will connect to ground. Okay, you will connect to ground. So they will not contribute any ones in the system. Okay. So if it is 10 bits, similarly, as many number of higher bits will be connected to the ground, or say 11 bits. So we will connect a higher number of 5 bits to the ground, and rest will be subjected to the parity checking. So X0 to X7 will go here, and X8 to X10. If we are talking about 11-bit parity checking, X8 to X10 will go here, and X11 to X15 will be connected to the ground. Okay, and we will take finally from here. So this is how we make use of parity and generation and checking. So to summarize, the output of a 2-input XOR gate is 1 when only one of the input is 1. For more than 2 input XOR gate, output is 1 if there are odd number of ones present at the input. Even parity refers to presence of even number of ones in bit patterns, and odd parity refers to odd number of ones. Parity bit is generated to make the bit combination that includes the parity bit one of even or odd parity, useful for transmission purpose and error checking and things like that. And parity in generation and checking involve multi-input XOR gate circuit. The similar XOR gate circuit can do both generation and checking. Higher order parity generator checker circuit can be obtained by cascading lower order circuit. We have seen one example, 2IC74180 generating 16-bit parity. Providing 16-bit parity generation and checking. And parity check is useful in detection of error when a group of bits is transmitted. Okay. So this is about this class. Thank you.